Hi, welcome to Spectral Signatures from Technology. My name is Vincent Kofman, and in this poster, I wanted to talk through some of the methods for detecting spectral signatures from exoplanets. And this work will be focused on Earth-like exoplanets, and we'll put this in the context of trying to find signatures from technologies. This is some of the work that we've been doing in the past. So this is Ravi Koparapu and Jacob Hackmishra and myself, and we've been looking for different signatures from technology that would be visible or may be visible in using future observatories in exoplanets. The poster will be shared online, but I wanted to talk through the steps here. There's three figures here, and we'll start with the first one. So the logic I want to go through here is we want to understand what we can detect with using current telescopes, and then using that we will extrapolate what we need for observations and what we can see with potentially future observatories such as the Habitable Worlds Observatory and the LIFE mission. In this diagram, you see the Earth mass on the y-axis, and you see the orbital distance on the x-axis, and the different dots here mark different exoplanets found with different observational techniques. So transit in red, radial velocity in blue, microlensing in orange, and direct imaging in green. So at the top here. And then what I really liked was this review paper that showed what James Webb has been able to do for us for exoplanet spectroscopy. It's about a year old now, but what we're seeing here is essentially the transit planets that have been observed using the James Webb Space Telescope, and then the direct imaging spectroscopy planets have been observed with James Webb. And you can see how much of the diagram essentially just populates and how much of this diagram it essentially doesn't cover, right? So we presumably we have a lot of planets here that we're just not sensitive to. If we now want to study spectral signatures from exoplanets, we need to understand what the current limitations are. And then, as I said, we go to future telescopes and compare that. So current limitations, these is nothing really refined here, but I was just looking at sort of the error bars on some of the observations. 10-5 for transits, 10-6 for current direct imaging observations. If we want to be looking at the Earth directly, we will need transit sensitivity is 10-7, which honestly might be a problem since that is not something I think we have the current methods to analyze the starlight subtraction well enough. But then direct imaging future observatories may be able to go down to 10-10. So we're talking about the Habitable Worlds Observatory here. LIFE does something similar in the infrared, but the contrast ratio is slightly different there, but the details don't matter too much. And now what we want to look at is two different types of spectral signatures. We're looking here at something very specific. So the question that Jacob had been asked, or he'd been asked by people, and it's something that we've been wondering is like, okay, we have very specific signatures from technology in the forms of radionuclides. So nuclides, radioactive nuclides that can only be formed through technology. How detectable would those be? So here we take the example of hydrogen iodine. Iodine is one of the fallouts from the Chernobyl disaster. For instance, it's one of the atoms that gets produced most. So it's it's poisonous, but it's very reactive. Thank you. And the signature is very specific because you have the HI molecule, and the changing the mass of the iodine will make a very big difference in the spectral offset. You will have to zoom in on the poster to see this, and that's kind of the point. If we're looking at HI in the Earth's atmosphere, what I needed to do was really disable all of the other molecules in the atmosphere to just look at HI. And then you see here at 4.2, there's a tiny bit of signal, and 2 point something, there's a bit of signal. But this is only the main isotope, and I had to increase the abundance by a factor of 1,000,000. So even for something that is very specific and relatively well observable in terms of the molecule or the atom will be in the atmosphere, it wouldn't be on the surface, so that makes detectability a little better. This will be a great challenge. So I invite you to have a look at the paper for more details. But remember, it's a challenge. That's kind of the main conclusion of the paper. And then in the other work, which with Ravi led, we were looking for solar panels as a surface feature. Let's say we changed parts of the planet, we covered with solar panels, and we see how much that changes the reflectivity of the current Earth. So current Earth here shown in black. Well, we add 2.3% of the Earth's surface at the equator. In solar panels, we see that there is a slight difference in the signal, and this is something that we may or may not be able to detect with Habitable Worlds Observatory. These are relatively strong signals and potentially detectable. The challenge here, however, is that it's not a very specific signature. and just a decrease in reflectivity because solar panels absorb all the light is very hard. So we try to look at there's a specific silicon edge further in the UV, but that is covered essentially by other absorption features, so it'll be hard to detect. So the main conclusion here is following the current observatories, see how far we still have to go. So we have about a factor of 1,000 before we can get to observing Earth-like exoplanets. And then spectral signatures from these will be challenging to observe. But I do think there's a lot more options than the ones that we've shown here. And I would just invite you to have a look at these methods and see whether they are useful for any of your analysis. I want to thank you for your attention and take care.